don't leave the show. All right, so now let's begin, guys. We got to discuss work, energy and power, and we'll directly go into our main agenda. And the main agenda here is this, that if I want to calculate the work done, by definition that is F dot delta R, if this is for the constant force. If you have constant force, the work done is the dot product of force and displacement. R vector is the position vector and change in position vector is displacement. So delta R would be the displacement. And what if the force would be variable, that is going to be integral F dot dr. That will be the case when the force would be variable. So this is the situation when the force is variable. So now let's start with the numerical part. Let's begin. And just to begin with the first question, let's say that I have F vector equals to x I cap plus 2y j cap. Now you need to decide that the force is constant or variable, and don't expect I give you this question. I give you F vector and I give you the initial position, final, and to calculate the work done. That would be very kidding, right? So it's better we start with this x I cap plus 2y j cap, and you need to calculate the work done from displacement 0 0 to 1 comma 2. Please do with this. Kritika, Yokit, Sai, Vaishnav. So guys, please calculate the work done for this. Okay, so to calculate the work done, we'll go in this way. That is integral x I cap plus 2y j cap dot dx I cap plus dy j cap. The first thing is that we're going to write f dot dr, we'll write that, okay? F dot dr is what we'll write. And the limit, of course, we'll put the limit later on. Now the first thing is, say x dx would be x square by 2 plus y square, and we'll see the limit 0 0 to 1 comma 2. So that's what we'll do. And after putting all those limits, now let's say this is going to be the upper limit 1 by 2 plus 2 to 4. That's what you get. So 4 to 8 plus 1, 9. So 4.5 joule is the work done by this force in displacement from 0 0 to 1 2. Okay. Any of the students having I would be happy if I would get your answers as well. That was very much essential. No problem. So this is how we compute the work done if the force is variable, F dot dr. This is how you need to move. All right. Now let's go with other parameter now. Let's try to go with the other part of the question. And the other parameter, what I expect is something like this. There is a certain situation where you need to calculate the work done in a constant force, And that makes the matter quite simple. Great, I got it. Harsh, Anu, Shivansh, Uma, Prachi, Deviswa, Adityan, Kritika, Ambika. All right. Okay, now see. Specifically, work done by a constant force is F dot displacement. So how are you going to write that? F delta R cos of theta. Force into magnitude of displacement into cos of theta. That's what you write. So you find the actual displacement and you multiply by the cos of angle between force and displacement. That is what we do. But this can also be written in this way. This work done can also be written in this way. That is force multiplied by the displacement along force. Now for you it should not be a much challenge to understand because you have been doing with dot product and you know the significance of that. So not the actual displacement, the displacement along the force, and no cos theta, because delta R cos theta, because this delta R cos theta can be visualized as displacement along the force. So one way what we did was that, say you visualized in this way that delta R cos theta is the displacement along the force. There is also another way how you can visualize, and that is F cos theta, and that's going to be the force along the displacement. Yes, so we can also write it in this way. That's also alternatively force along the displacement multiplied by the displacement. So people, it's all equivalently the same. Either you go through this way or this way. Now the big question may come that, all right, we are loaded with all these principles. Now how are we going to find out that we will be applying this thing? It's very easy. If you get this situation, the hint would come itself that, all right, we need to approach in this given way. That's not a difficulty. I'll show with an example and we'll do a couple of examples, so you need not worry. The first thing is, say, from a certain cliff, if you see the height is h, a particle of mass m has been thrown with a speed u from a certain cliff, and you know, due to this it goes and it enjoys its parabolic trajectory, right? That's how it goes. And I'm not interested in other calculation, but I just want the work done by gravity. Please do this. I'm not interested in other, I said. I just want work done by the gravitational force starting from here to here. Please think about that. Come on. MGH, not MDH, MGH. Okay, so people from North India can understand MDH. This is MGH. Okay, that's great. Let's see, how did we do that? Let's try to understand. As it goes from this to this, look, this is the distance, while this is the displacement. The displacement is this. This was the distance while the displacement is this. But I would rather go in a different way. I would go with this. That is, I'll be using this pattern, say, force mg multiplied by displacement along the force. And displacement along the force would be plus of, or just to make it more simple, y displacement. Why? because the force is along y-axis. So displacement along the force, that means y component of the displacement. Yes, I use this force into displacement along the force, mg into y displacement. So viewers, remember, from here to here this is the displacement, but I'm interested in the y displacement, and that y displacement is h. So work done by that is going to be plus of mgh. All right, now let's see for the next one. So that part was quite a simple one, that should not be trouble. Okay, so here all right, something like a 50-50% division, bisecting. Now here's the question here. The question is something like this, people, that there is a pendulum which is hanging, and this is mass m, this length is L. There is a pendulum of mass m, length L is the length of the string. An external force is there, and it is guaranteed that this force is always along x-axis, Fi cap. But due to the force, you know that the string will start getting inclined, and by the time it reaches there, this angle, let's say, is 60 degree. By the time it reaches there, people, you got to calculate work done by tension, you got to calculate work done by mg, and work done by F. You need to calculate work done by each of the force. Please do. Kinetic energy is not changing. Which question? This one? Tushar, just immediately please say which question is it you're talking about, kinetic energy not changing, Tushar? If you're talking about this thing, meanwhile, let me answer, Tushar. We can't comment just by observation that kinetic energy is not changing. It may be moving with an accelerated one, or even if you say that, all right, net kinetic energy is constant, but individual force may do the work. The net work would be zero, even if you assume that kinetic energy is constant. All right. Previous one, the mg, the projectile, the kinetic energy is certainly changing because the speed increases as you reach the bottom. Work done by gravity, mgl by 2. Prachi, a bit of mistake. All right, people, now let's see. Come on, I'll give you 1 minute more. Okay, so I've started getting options. Now let me do it. It's something like this. Look, if I want to calculate first work done by tension, now this goes in this way. And remember, tension is variable, because forget about the direction. Even in the most primitive case, the direction of tension keeps on changing, right? So tension would be variable. Forget about magnitude. The direction varies. So what will I get? I will get, for the tension, work done by tension is integral F dot dr. Then you find the angle between force and tangent is the velocity, is always 90 degree, because angle between force and this, so that work done is going to be 0. So the first part has been done. What about work done by mg? Mg is a constant force. So if I see work done by mg, that will be mg into y displacement, but a negative sign you need to add from your own part. Well, if you do in terms of cos theta, then that obtuse angle is automatically going to take care of the direction, if you go by the original one. But then here you're just seeing all those components and projections. So therefore you need to understand, you need to be very, very careful while putting this sign. So you need to keep the negative sign from your own part. That is very must. And let's say now, this is the y displacement is this much. The actual displacement is there, that's fine, but the y displacement would be, and you can use simple geometry. This is L cos 60, which is L by 2. So this is going to be L by 2 there. So this work done equals to minus mg multiplied by L by 2. So that will be work done by the gravity, work done by mg. Now work done by the external force. If I want to calculate the work done by external force, if I want to find that, the external force is acting here and the displacement is this. That's how it comes. Alright, because I require the x component of the displacement. This is F and I want the x displacement. That's what I want. And then this comes out to be F and the x displacement is L sine 60. So that is root 3 L by 2. So that will be the total work done by the force, and that is going to be positive because the force is right, the x displacement is also towards right. Great. Kritika has absolutely answered everything in the correct way together with the sign. Lot many people have missed the work done by mg, and Anu Singh has again answered it correctly, the work done. So that's great of you people. All right, now one more thing. You need to understand that whenever you have an extended body and you need to calculate work done by gravity, so there always you need to take the center of mass. So let's see with a simple example, like let's say that there is a well, a deep well, and the road surface, so quite an unsafe one. This is the road and no barricading, so let's not worry about that. Okay, so we'll talk to the municipal people why did not they do the fencing. This is A, this is H, and let's say that the density of this liquid, the density is rho. Yes, please calculate the work done to empty the well. You want to empty the well completely, so calculate the work done. How much would be the work done required to completely empty the well? Please do. Work done by F. Avist certainly will do that. Aryan, why do we use Y component in mg? Because mg is the force along Y direction. So displacement along force. So since the force is in Y, displacement along force is Y. And Y the negative direction, mg is down, displacement is up, so there must be -1. And Abhis says, you want to understand work done by F? Certainly, because F is a constant force and that is always along x-axis, so F into x displacement. And x displacement is this. If this is L, this is going to be L sine 60, and that will be √3 L by 2. Abhis, hope this clarifies, answers your question. All right, now let me come up here. Work done to completely empty the well. As I've said, this is an extended mass system. And if it is extended mass system, you need to concentrate on the center of mass. That is very, very important. And the work done to completely empty the system will be mgh by 2. Because the center of mass is h by 2 below, so mgh by 2, and the value of m will be rho into A into h, density multiplied by volume is the mass, into gh divided by 2. So that will be the total work done to empty the well. I'll just give you a brief idea that why do we, empty means Tushar, that completely bring out the water and bring it on the ground. That is emptying. Okay? That's how we do it. Now let's go to the next thing. Empty. So perhaps, Tushar, you mean to say you need to empty the well. So you need to remove the liquid from the well. Where the liquid is after? On the field. Okay, so emptying, that's obviously understood. And Deveshwar, yes, outside the well. Navneet, rho agh square by 2. Rho agh square by 2. Great. Kritika, yes. And Abhist, all right. Tushar, rho agh square. One thing was missing, so please don't worry, but still, that's not a difficulty. This is how we compute the case. Now we'll go to another important thing, and that is, guys, it's called as the work energy theorem. And this is one of the part which is very, very important, the work energy theorem. And you get a lot of question, direct question, that's one thing, but you also get application of those questions, that's another thing. So in both the way, a direct question and the application, that really makes this topic very, very important. And this thing says, what does the work energy theorem say? The work energy theorem says work done by all the forces. Now don't say this is wall forces. Work done by all the forces is equal to change in kinetic energy. Remember, work done by all the forces is change in kinetic energy. Change is the word where I would like to focus. Work done is not equal to kinetic energy. That is equal to the change, the final kinetic minus initial kinetic. And kinetic energy has speed with it, right? So what do is that you can conclude one thing, that you can make a conclusion if work done is equal to 0. So it implies the kinetic energy would be constant. That is what it implies. If work done is equal to 0, it implies kinetic energy would be constant. And if kinetic energy is constant, it further implies the speed would be constant. People remember, it's not the velocity, it is the speed which is constant. So you get a direct connection that work changes the speed. What about force? Force changes the velocity and work changes the speed. Like acceleration changes the velocity, and acceleration and force are equivalently same. Velocity changes the position. Acceleration changes the velocity. So all those sort of changer, you know it. You got to be careful with that. So I'll just give you a small, like let's say, suppose someone says that force is present but work done is 0. We get this sort of situation. This is not a new thing, that you have force but the work done is 0. So if force is present, it means the velocity changes but work done is 0. That means the speed is constant. So this means only the direction is changing, because force changes the velocity, work done changes the speed. So presence of force guarantees change in velocity, and since the work done is 0, it means the speed is constant. Now it's an easy connection, a variable velocity with a constant speed, so that means the direction must be variable, right? So that's a very easy way you can deal with that. But that was just for the sake of formality. Now let's say with a question. Suppose a mass 2 kg body is there and x is 1 plus t square plus of 2t. That's a case. All right. That was a bit wrongly arranged. So let's say in this way. You need to calculate work done in first 2 seconds. All right. Let's do. Well, so that was given, that was, you may take it as cylindrical or cuboidal, that doesn't matter because area is given, h is given. So in both the case, cylindrical or cuboidal will give you the total volume. Navneet has texted his answer and that is 80. Let's see. So other answers are also coming, and meanwhile 81 is by Aryan. So Aryan stands a bit different from other people, but that's absolutely no problem in doing so. I don't have problem if you stand different. Tushar comes with 56. Now that is something quite different. Let's say work done in first 2 seconds. So it is something like this, that x is this much, so velocity will be 0 plus 1 plus of 40. That's a case. And work done in first 2 seconds, let's say. So I get velocity at 0 is 1 and velocity at 2, 4 to 8 plus 1 is 9. And work done is half into mass into V2 square minus V1 square. So that comes out to be 80 joule. Work done equals to change in kinetic energy. Good. Anu, Tushar, Gautam, Harsh, Adityan. Aryan, you missed one small thing, son. You had to subtract the initial kinetic energy as well. I had said very categorically that work done is not equal to kinetic energy. It is the change in kinetic energy. So Aryan, you got to be careful with this thing. All right. Next question now. Next question is this. A force time graph is given. All right. This is T. This is F. A force, let's not be so miser in this space. Let me take it here. This is T. This is F. A force time graph. Okay, this is how it goes. The force time graph. Let's see. This is 0, this is, let's say, 6, this is 8, this is 20, and this is minus 5. The value must be very clear. And a particle mass is 2 kg, that's also given, and it starts from rest. I think it's clear, right? The force is minus 5 here, the force is 20 here, 0, 6, 8. The mass of the particle is 2 kg, initial speed is 0. So you need to calculate the speed at t equals to 8 seconds. You need to calculate that. Please go ahead. You need to calculate the speed at t equals to 8 seconds. Yes. Okay, so let's say, meanwhile, if I start doing that, we need to calculate the speed at t equals to 8 seconds. And this is a force time graph. The moment I get a force time graph, trying to use the previous data, the area under force time graph gives me the change in momentum. The area under the force time graph gives me the change in momentum. Even if you haven't memorized it, you can easily see F equals to dP by dt. So dP will be F dt, and you can do that. And let's see the area under force time graph. So that is equals to half base into height is this, plus base into height, that's the area. So this is 60 minus of 10, so that's 50. So the change in momentum is 50. But you also remember that P final minus P initial is 50. You need not miss this important thing. It's a change in momentum. All right. Meanwhile, I got the option 25. Let's see. and initial momentum is 0 because the particle starts from rest. So I get the kinetic energy is p square by 2m, and p square is 2500 by 2m, so that is 4. I'm getting something different answer. All of you have, strangely, all of you have voted 25 as the option. I don't know where you got that 25 from. Okay, so p square by 2m, p is 50, so 50 square, 2500, I think this is going fine. 4, 6, 25, 24, 4, 2, 8, okay, that's a guess. So 625 joule is the kinetic energy, and if that is the kinetic energy, work done will be equals to 625 because of the fact we know work done is change in kinetic energy. Now this is quite interesting. I'm not able to figure out that why all people have got the same answer 25. I'll just try to see where did you make the mistake, if at all. See, I'm not able to find out why did you get 25. That has been a mystery for me, but all right. So 625 is the work done. Okay. All right, now let's go for the next part. A very tricky question here. You will have to understand the context of the question, and let me write the question for you. It's a bit tricky. It is this: a particle is subjected to external force F. All right, a particle has been subjected to external force F that is given. For a displacement x, I hope you'll be able to understand my handwriting. For a displacement x, the kinetic energy, we'll have to talk about the kinetic energy, is this: directly proportional to m, b directly proportional to v square, c directly proportional to m raised to the power 0, directly proportional to x. And this is more than one option. So if I go for more than one option, that is the case. Okay, I asked the speed. Thank you very much. Thank you. Thank you very much. The final speed, that's great. So I hadn't realized that. Thank you very much. Yes, Aryan, you can calculate, you can solve it by integration. You can solve it, but don't do that, because if things are so easy, then if it can be done so easily graphically, then why to take unnecessary trouble? So don't try, I mean, don't be adventurous. Okay, A and B. Kinetic energy depends on M. So let's say A, B, A, B, A, B, A, B. Okay. Now, I was just waiting for people's option. Directly proportional, one thing. Anu Singh says D. Rest all will go for A, B. And Abhist says A, B. Aryan says B and D. Let's see now. In fact, I will go with option chosen by Anu Singh. That would be option number C. It does not depend. Option number D. And even C is correct. So C and D would be the correct one. M raised to the power 0 directly proportional to X. So I'll go with C and D. And Ambika. So is this Ambika Batra? So perhaps C, D. Let's see. And let's see how it comes. Now just realize one people. Realize one thing. You are not understanding the context of the situation. You're just saying, okay, kinetic energy is half mv square. So directly proportional to mv square. No, you need to understand the context of the situation. And let me tell you how the context goes. In order to understand this thing properly, I'll have to give you the example. Let me give an example. Suppose there's a family, and in this family, you know, X is the head of the family. So whether father or mother, that doesn't matter, but X goes to earn, and X is the person who brings the earning to run the family. Now just see very carefully. X goes to the office, let's say, and works, and X brings the money. Now just see carefully. How much X earns, the earning of X depends on what X does in the office. It does not depend how many kids are there, whether one child or two children. It does not depend. Okay, the earning comes to the home. And if there is one child, if there is two child, the division would go in that way. So this is where you need to understand people. How much X earns does not depend on how many family members are there. It really depends on how does he work there. All right? And he brings it, and that is shared among the participants. That is shared. So that is the point you need to understand. Well, it's a psychological issue that if X has two children, then he should be motivated to work better. That's a psychological one. Unfortunately, this is physics, so we'll not be talking about that. So now just understand the sequence of the event. The sequence of the event, when you understand people, is the work is done by Fx, and this work gives the kinetic energy. Initial kinetic energy is 0, and that kinetic energy is half mv squared. So just see, look at the sequence. A particle is subjected to external force. The force does the work. That work gives the kinetic energy. So kinetic energy does not depend on this. The kinetic energy provider is not this. The provider of kinetic energy is the work done. Well, if you have that kinetic energy now, how much would be speed for two different masses? If you want to find, you may use this relationship. But this is not the provider of kinetic energy. This is the expression. So like here, the children are now the provider of the earnings. The earning comes from the office, and that is distributed among the children. So the idea is exactly same. So therefore, option number C and option number D would be the correct option, because that kinetic energy depends on the work, all right, and not on the mass and the speed. So this part you need to understand. Just think carefully, where is that kinetic energy coming from? that will not be a trouble. Okay. Now, after we have done about the concept of work energy theorem, now it is something like this. Say, let us see one simple example. For example, you would get a very beautiful thing here. The direct application of work energy theorem. This is height h and there is a block of mass m. So this is how it goes. And the surface is purely smooth. The surface is smooth. Try and think in terms of work energy theorem. Try and think that if the initial speed is 0, what would be the speed of the particle by the time it reaches there? Try to think in that way. You need to calculate it. The surface is smooth. Just think. Okay, root 2gs, root 2gs, root 2gs. That's great. So let's see how to come up with that conclusion. Let's go step by step. The situation says work done by all the forces. So work done by mg plus work done by normal reaction is change in kinetic energy. What are we applying? We are applying the work energy theorem. The normal reaction will do 0 work because at every point the normal reaction is perpendicular to this. Having said that, please don't draw conclusions saying that work done by normal reaction is always 0. I can show you plenty of situations where normal reaction may do non-zero work. And the best way is that, let's not be very complicated, a simple way, there is a platform, there is a block of mass m. If the platform goes up, the normal reaction is acting up, the displacement is acting up, so the work done by normal reaction would be positive, right? That's how it goes. So you can't generalize saying that normal reaction always does 0 work. It may do, it may not do, it depends upon the situation, so you need to be careful with that. So here guys, the normal reaction is always perpendicular to the displacement. So work done by normal reaction would be 0. At least in this situation, it's perpendicular. So the work done is 0 in this. Work done by mg, we had seen that's plus of mgh because as it goes down, it's a constant force. And here, kinetic energy is change half mv square minus 0. So you can go with V equals to root 2gh. That's great. Now once we've understood about the kinetic energy, we will be going to the next term, and that is potential energy. So all of you must be, certainly you must have done all about the concept of potential energy, that the energy depends only on the configuration. The energy has nothing to do with other things, so that's perfectly fine. But one more thing, let me tell you. Potential energy is defined only for, I've seen only few people take this thing in mind. So this is defined only for conservative forces. Potential energy is never ever defined for non-conservative forces. It's defined only for conservative. Like mg is a conservative force, so you have gravitational potential energy. Spring force is a conservative force, so you have elastic potential energy. But we never have tension potential energy. We never have frictional potential energy, because these guys are the non-conservative. So non-conservative force will not have potential energy with them. The conservative one would have the potential energy with them. So just keep this thing properly in your mind. And how much is the potential energy? How is it defined? It is defined in this way. Work done by conservative force is minus of delta U. Now look at the primary difference between the work energy theorem and this. The work energy theorem says work done by all the forces is change in kinetic energy. All. It doesn't matter conservative, non-conservative, anything, whichever comes, all welcome. Work done by all the force is change in kinetic energy. However, when it comes to potential energy, work done by conservative force, only conservative. That's why I had said that potential energy is defined only for conservative. And work done by conservative force is minus of delta U. So what does that mean? It really means that if work done by conservative force is positive, it implies delta U is negative, and it implies the potential energy decreases. So that's a point you need to be very, very careful. Look at there. It's obvious. You don't require much theory for that. If that is positive, delta U is negative. Delta U negative, potential energy is falling, right? That's how it goes. And converse is also true. If work done is negative, delta U would be positive, and if delta U is positive, that means potential energy rises. So that is how we relate and we predict whether potential energy rises or falls. A very simple example, just see, when a ball goes up, the work done by gravity is negative. We know that. When a ball goes up, the work done by gravity is negative, and if work done by gravity is negative, that means potential energy will rise when a body goes up, and that's a fact. So it was just a verification tool. So remember the primary difference between the work energy theorem and this. Work energy theorem says work done by all the forces, while for potential we talk only about work done by conservative force. So be very, very careful with this situation. All right. Okay, now the expression must not be new to you people, because the potential energy, you write it as plus mgh if it's height h above and taking reference as the ground, all those story, plus minus mgh. So plus mgh if it is h above the ground, minus mgh if it is h below the ground. So that's not a problem. And potential energy of a spring, that's not a problem. That's 1/2 k x square, where x is always measured from the natural length. Where x is always measured from the natural length. In other words, this x is the elongation or compression. You got to be careful with that. And elongation and compression is always measured WRT, natural length. So that is obvious fact, and that you understand. All right, people. Now let's go to other situations. Now after this we have another term, and that is the mechanical energy. So this is mechanical energy. So what is that mechanical energy? If I denote it by E, that mechanical energy is the sum of kinetic and potential. This is the case. Mechanical energy is the sum of kinetic and potential. Okay? Now, how do you get, say? Remember one thing. Saying mechanical energy and saying total energy is very, very different. Total energy means the heat, light, sound, any other form. That is the total energy. But mechanical energy means only the sum of kinetic and potential. So you need to be very careful with that term. And now let's see. Just see carefully. What does work energy theorem say? Work done by all the force is change in kinetic energy. This is work energy theorem say. So work done by all the force, let me divide it into two parts. One is the dissipative plus work done by conservative. So okay, if you want to write it as non-conservative, I'm perfectly fine with that. Work done by non-conservative plus work done by conservative will be equals to delta K. It's the same thing. The total force have been classified into conservative, non-conservative. That has been done. All right? It has been classified into conservative and non-conservative. And work done by conservative is minus of delta U. So I get work done by non-conservative is minus delta U equals to delta K. That's what you can write. And work done by non-conservative, you get delta K plus of delta U. And you suddenly realize that delta K plus delta U would be delta E, because by definition E is K plus U. So this is the change in mechanical energy. So the change in mechanical energy is there, work done by all the forces there, and by the way, work done by conservative force minus delta U. Let me just write it here, by the way. All right, this is here. So I'm just listing up these three parameters. They are very frequently asked and students often get confused with this. So be careful with this part. Now let's go to the mechanical energy part here. Work done by non-conservative and so, right? Okay, people, now first thing say, just try to understand here. If work done by non-conservative is 0, that's a case. Suppose I make that claim that work done by non-conservative is 0, or I say the body moves only under the effect of conservative force. It's the same thing. It's the same thing, guys. Either you say there is no non-conservative force at all, only conservative. Either you say that, or the second, despite non-conservative being there, the work done is 0. All I want is work done 0. So how is the work done 0 guaranteed? Either the non-conservative is not there at all and work done by non-conservative. All right? How do you guarantee the work done by non-conservative is 0? Either non-conservative is not there, or despite being there, the work done is 0. That's what I've written, nothing more than that. And if this non-conservative work done comes out to be 0, it means delta E would be 0. And if delta E is 0, that means mechanical energy is conserved, right? That's how it goes. So here we say that is delta E will be 0. That is mechanical energy would be conserved. So remember, mechanical energy is conserved under this condition, while kinetic energy is conserved when total work done is 0. Be careful about the kinetic energy and mechanical energy. These are all, I should say, theoretical question, but they really play a very important role. All right, another question, let's see. And this time even let's bring the spring buddy with us. And here is the first one. The spring constant is K, and here is mass M. It comes with a speed U. Surface is smooth, and you need to calculate the maximum compression. You need to calculate that. Please do. U root M by K. Tushar, you make point. Yes, you're right. U root M by K. Kritika, that's fine. Shivansh, Oja, that's right. Okay, now say this situation involves one non-conservative force, that's normal reaction. How do you classify conservative, non-conservative? I'll give you a simple clue. Gravity, conservative. Spring force, conservative. Electrostatic, conservative. These are the conservative one. Gravity, spring force, electrostatic. All right? And rest would be non-conservative. Normal reaction is acting, but the work done by normal reaction is 0. So you would get work done by non-conservative is equal to change in mechanical energy, and this is equal to 0. So it means Ki plus Ui is Kf plus Uf. This is how it goes. Initial kinetic plus initial potential is final kinetic plus final potential. There is no requirement to include gravitational energy, because the height is not changing. What is initial, that is equal to final, so that will get cancelled out. So there is no point to unnecessarily extend. So this is 1/2 mu square plus 0 is 0 plus 1/2 Ka square, because maximum compression, if I say A is the compression, at that point the value of speed would be equals to 0, right? The speed is 0. So yes, at that case the kinetic energy is going to be 0. That's great, and people have solved it. Now another question. Here is a spring, and this spring is in a natural length. All right, the spring was given and the spring is in its natural length. The spring constant is K. The spring constant is K. N, I hung a block here. When it was in natural length, a block was hung. Now this block will go down. I repeat, when it was in natural length, it was hung. So you need to calculate the maximum elongation. You need to calculate the maximum elongation. Please do that. Tushar, that's right. Great, Tushar. That's great. Okay, so meanwhile I'm waiting, but let's say this is the maximum elongation. And maximum elongation, what would be the characteristic? Here the speed is 0 because it is released. And the maximum elongation means the speed of the particle again will be 0 here. That's how we understand maximum elongation. The meaning of maximum elongation would be the speed there is 0. So that's why you call it maximum, and after that it would go back. Now let's see, this time even the gravitational potential energy has to be included. Reason being obvious, because the height is changing. Now is there any non-conservative force involved? No, because the situation has only two forces. One is gravity, other is spring force. So since only conservative force is involved, so we simply write the delta E is 0 because only conservative force is involved. That means mechanical energy would be conserved. You may write it in the same way, EI equals to EF. Now let's see. Initial is this. So that's Ki plus Ui gravity plus Ui spring is Kf plus Uf gravity plus Uf spring. That's what you get. And now Ki, the initial kinetic energy is 0. The initial kinetic energy is 0. Ui, the initial gravitational energy is 0 because I assume this as the reference. That's not a point for gravity. Initial spring energy is 0. Final kinetic is again 0. Lots of 0 coming on. Final gravity minus mgl, let's say L is the elongation. And the final spring energy is half kl square. Notice one thing, gravitational energy was taken negative because with respect to the reference it falls down. With respect to the reference it falls down. So gravitational energy is taken as negative. But the spring energy, whether it's elongation or compression, the spring energy will always be half kx square, and since that is squared, that's always going to be positive. So you need to be careful. And we solve this, L you get as 2mg divided by k. So that is the maximum elongation of the spring. Be careful with this point. Be careful with this point. Not mg by k. Lot many people do this, KL equals to mg, and you get L equals to mg by k. Let me just tell you where is the mistake if you do KL equals to mg. KL equals to mg means you are doing net force as 0. Yes, KL equals to mg means you are doing net force as 0. While maximum elongation means velocity there is 0, not the force. So as a matter of fact, KL equals to mg comes here. You could say, if you do KL equals to mg, L would be mg by k, and mg by k comes here at the half of 2mg by k. So be very careful. Net force equals to 0 is something else. Speed equals to 0 is something else. So at maximum elongation, the net speed is 0, not the force. Be very, very careful with this point. Alright, so that was about the situations, how you discuss. Now let's go to the next term, and that is the power. So that power is in fact how fast or how slow a work is done. In order to measure that, we have power. I repeat, how fast or how slow a work is done. In order to measure that, we have power. Now it's something like this. I'll give you a simple idea. Imagine a block of mass m has been raised up to a height h. The work done is how much? Aryan, why was u initial 0? For gravity, I assumed this to be 0. For gravity, you can assume anywhere as the reference. And Aryan, for spring, the natural length is taken as the reference. All right? Now, as I was saying, a block of mass m has been raised up by a height h. Suppose it takes 1 hour for person A and 5 hours for person B. Now, whether 1 hour or 5 hours, the work done is same, mgh. But in the first case, the rate of work done was higher because in the smaller time, a greater work or the same work was accomplished. So, whenever we want to discuss power, power is how the work is done, how fast is done, how slow is done. The same work done in a lesser time, power would be high. Same work done in a larger time, power would be less. The rate of work done. And how do we define the mathematical formula? The mathematical formula is this: average power is the total work done by time. A span of time. In that time interval, how much is the work done divided by the time, that's the average power. And what about the instantaneous power? That is F dot V. So instantaneous power means the power at that instant at which you are interested. Let's see with the help of a question. So F is the force whose power you are interested to calculate in. V is the velocity at that instant in which you are interested to calculate the power. So instantaneous power, the instant where you are calculating the power. So that has to be understood. So now let's see. Arun, RHS you want to explain? Okay. The maximum elongation Arun, kinetic energy is 0. The gravitational potential energy, because that was taken as the reference, so it goes L below the reference, so minus mgl, because we are taking gravity as this reference, and the final spring energy would be half k L square, because the elongation is L. That's the case. All right, Arun. All right, so this is the situation. Do with a question, please. A projectile has been thrown. A mass is m, the speed is u, the angle is theta. The angle is theta. And from P to Q, let's see, I need the average power in the duration PQ. Average power developed by what? By gravity, of course, because there is only one force involved. So that's understood, mg. Please do. A projectile thrown in this way, you need to calculate the average power developed by gravity. Please do the calculation. All right, the average power developed by the gravity between P to Q, that is equal to work done by gravity by the time. And let's see, from P to Q, the work done by gravity is minus mgh, and time is half of the time of flight. Time is the half of the time of flight, because it is the time taken from P to Q. And then solving it, we get the average power is minus 2 mgh by t, and that is minus 2 mg. The height is u square sine square theta divided by 2g, and the time of flight is 2u sine theta by g. So whatever is the value comes, that will be the average power developed by the gravity between P and Q. All those sort of calculation can be done. Okay, minus mgu sine theta by 2. Let's see. Let's see the calculation. All right. So this is 2 and 2 gets cancelled. G and G gets cancelled. U sine theta. All right. So that is minus mg u sine theta minus mg u sine theta by 2. Yes, Navneet? Bravo. That's a wonderful thing. Great, brother. So that is the average power developed by the gravity between P to Q. My next question is calculate the power developed by gravity at Q, at that very instant. So that is instantaneous, not an average. You got to calculate the power at Q, at that very instant. Please do the computation. Move ahead. Ambika had got the same answer, mgu sine theta by 2. Great, Gautam Jayant, that's great. You know, answers keep on coming. That's a fuel for a teacher. Otherwise, I'm here in a room and just teaching. So I want the option. That is very important. That energizes me.